Significant figures are the certain amount of digits used in a number to express a certain degree of certainty. So how do we know what sig figs should be counted? Let's have some practice. Write most digit as our estimated uncertainty. So let's look at our problems here. So for say 3.201 would have 1, 2, 3, 4 significant figures. Okay, so then we look at 8.9009. Notice how there's 2 zeros in between the 2 nines. You'll have 1, 2, 3, 4, 5 significant figures, and once again, the zeros are significant because they are between 2 non-zero numbers. All digits will be significant except for the non-zero. We start by looking at our decimal place number, counting from left to right, looking for our first non-zero number. Once you find your first non-zero number, all digits to the right of it will be significant. However, we must be aware of the zeros and where they are placed. If a zero lands before or after a decimal, it is considered significant. So let's look at our example. We have 1.1300. Since the zeros are coming after two significant numbers and after a decimal, we will consider them as sig figs, and therefore we will have 5 significant figures. If the number being observed does not have a decimal point, then all zeros will be considered non-significant. For 300, we will also cross out the zeros and only end up with 2 significant figures being the 4 and the 3. Zeros before a terminal point will also be considered significant. So when we look at the example 5400, the zeros will also be counted as significant since they are right before our decimal. Therefore, we will have 4 significant figures. So now that we have learned about significant figures, we will get into chapter 2, which is naming acids and anions. So what is an acid? An acid is a compound in which one or more H+ ions are bonded to a negative ion. Whenever we are looking at the bonding of hydrogen ions and negative ions, we must remember that the charges must balance out. So when we're looking at hydrogen fluoride, we will notice that there is one H and one F. So since the H is a plus, the fluorine must be a negative. So it's a 1-to-1 ratio. When naming acids, we must consider that they are named after their anion or their negative ion. They form when they dissolve in water. Then, all depending on the specific hydrogen atom the ion bonds with, we will run into different naming of ions. When working with simple binary compounds or simple acids, which are acids without oxygen, they will have only one anion and one hydrogen atom. The anion will end with the suffix "ide." So let's look here. It's hydrogen chloride. And its acid name, on the other hand, will start with the prefix hydro and end with the suffix ic. So for example, we have hydrogen chloride. We will turn it into hydrochloric acid. And however, when focusing on acids that have oxygen in them, oxyacids, the negative ion will be polyatomic ions. We will follow by certain rules. Polyatomic ions that end with the suffix ate will be switched to the suffix ic. Now let's look at some examples. So we have hydrogen nitrate. Whenever we are working with the ates, they become ic. So then we would have nitric acid. We would be ignoring the hydrogen. Now let's look at how we name acids with the polyatomic ions that end in ite. So we have example here, hydrogen nitrite. The ite will become OUS. So then it would become nitrous acid. It may be hard to remember how to rename all these acids with polyatomic ions and individual elements, so I created a quick mnemonic to help you in the renaming of them. From going with ide to ic, ate to ic, and ite to OUS. So it would be, my ride has hydraulics. And we have I ate something icky, and Sprite is delicious. Into the prefixes per and hypo. So here we have a variation of polyatomic ions with chlorate, chloride, and hypochlorite. So the prefix per would be used for the ion that has the most oxygen atoms in them, and hypo would be the one with the least oxygen atoms in them. So now that we're looking at HClO4, hydrogen chloride, it would be perchlorate because it has the most O atoms. And then we have ClO3, which would be chlorate. Then we have ClO2, which is chlorite. And then we get to the atom that has the least amount of oxygen. And it would be ClO minus, which would be hypochlorite. And I will now present to you Danielle with stoichiometry.
Stoichiometry, in literal terms, means measuring element. As you can see, stoichiometry can be used in many different situations, such as measuring ingredients while cooking, changing molarity in a substance, and even calculating how much substance of methamphetamines should cost, as we see in the clip of Breaking Bad.
And you got, Jesus, you got crystals in here 2 inches, 3 inches long. This is pure glass. You're a goddamn artist. This is art, Mr. White.
Actually, it's just basic chemistry, but thank you, Jesse. I'm glad it's acceptable.
Acceptable.
Stoichiometry is used during experimental procedures in which one must calculate the products and reactants of a reaction using molar-mole or molar mass ratios. As Avogadro's number is the amount of substance that contains the same number of atoms in a 12-gram carbon-12 atom. Okay, so we're going to start off with the easy problem of how to do stoichiometry. So our question is, what is the mole of iron if the mass is 95.8 grams? So the first thing we want to do is create a roadmap. So since we're trying to find the moles, we're going to go from mass to mole. Then we have to pull out a periodic table and find out what the atomic mass is for iron. And what we know is that iron's atomic mass is 55.8. So then we take the 95.8 grams that's in the calculation, or in the problem, and divide it by the 55.8 grams that iron weighs. So what this tells us is for every 55.8 grams of iron, there's 1 mole. And since mole is what we're looking for, we're going to take the units and cross them out for grams so that it only leaves us with mole. So when we divide this, we get 1.71 moles of iron for every 95.8 grams.
Action.
Okay, so since we found out there was 1.71 moles of iron in 95.8 grams of iron.
So chapter 4 is about the 3 chemical and the complex part that water plays in aqueous chemistry. So to start off, I want to explain the differences between strong electrolytes, weak electrolytes, and non-electrolytes. So strong electrolytes usually completely dissolve in water. Weak electrolytes partially ionize when they are dissolved in water, and non-electrolytes do not dissociate at all. So here's an example of strong electrolytes, and they completely dissociate and they have no tendency to recombine again. Weak electrolytes, this reaction is significant in both directions because it's said to have chemical equilibrium. You see, as they do not dissociate completely like strong electrolytes. And non-electrolytes do not dissociate at all in water, and some of the examples are sucrose, ethanol, and more. So chapter 5 is about gases and kinetic molecular theory. So as we know, the 3 different states of matter are solid, liquid, and gas. And these are examples of the different states of matter. So solids and liquid have smaller changes, and gases alter significantly by changing the applied force or temperature. So here we have a liquid and a gas. I mean, two liquids, but the soda contains carbon dioxide, which is a gas, and that's why it's going to be more reactive. So here we're going to put elementals in the water and see how it doesn't really react. And now we're going to add the elementals to the liquid that contains carbon dioxide. As you can see, it didn't react a whole lot because we didn't put a lot of gas, but it started a bubbly, which is the reaction.
What's up, YouTube? Today we're going to be talking about enthalpy and electromagnetic radiation and atomic spectra. So enthalpy is the thermodynamic variable that relates to the change of energy at a constant pressure. From the above stated example, the constant pressure will be the pressure from the stopper, and the change in energy will occur due to the liquid being heated up in the Bunsen burner. So we're going to do one problem called finding the enthalpy of the solution. So the enthalpy is represented by a change in H, which is equals to mass times specific heat times a change in temperature. So for this equation, we're going to use the reactants 2H2 plus O2 to give you the product of 2H2O, which is water. So for step 1, we're going to find the mass, which is M. So to find the mass, we're going to ignore the reactants because this really isn't as important. So we're just going to look at the products because the product is water, and that's what we're trying to find. So to find we have to find the molar mass. So the molar mass of hydrogen 2H2 is 4 grams, and then of oxygen, which is 2 oxygen, 16 times 2 is 32 grams. So we add them to get 36 grams. So we have our value for M, which is mass. Second step, we're going to find the change in temperature, which is represented by this equation. Change in temperature is equals temperature 2 minus temperature 1. So in this equation, we're given that temperature 1 is 185 Kelvin and temperature 2 is 95 Kelvin. So we can just plug in chart and subtract. So it's just basic mathematics. So 95 minus 185, which is equal to negative 90 Kelvin. So the step 3, we're going to have to find the specific heat. So since we know the product is water, H2O, so we already know because the specific heat of water is 4.2 joules per grams. So this is how we got it. So we're going to combine the whole, plug in the whole thing we got from the mass, the specific heat, and the change in temperature. For the mass, we got 36 grams. For the specific heat, is 4.2, which was already given. And for the change in temperature, we calculated and came out to be 90 kelvins. So in order to get joules, we have to, this grams, 36 grams cancels with the grams on the bottom. So you're only left with joules. So when you multiply 36 times 4.2 times 90, you get negative 13,608, which is your final answer, which is equal to enthalpy.
So for the Lewis dot structure, there are a couple of steps in order for it to be done. So basically, first you have to find the total number of valence electrons. Step 2, you have to find the number of electrons that need to make the atoms happy. And step 3 is determine the number of bonds in the molecule. Step 4, choose a central atom in order to draw the skeletal structure, which is step 5. And finally, place the electrons around the outside atoms. I'm going to write the formaldehyde CH2O Lewis dot structure. So step 1, in order to find the total, we find that in the molecule we have 1 carbon, which has 4 valence electrons, 2 hydrogens, which has 1 valence electron, and 1 oxygen that has 6 valence electrons. So 4 plus 2 plus 6 equals 12. So in total, the molecule has 12 valence electrons. Step 2, well, the atom's happy. The carbon needs 8 valence electrons, hydrogen needs 2 valence electrons, and oxygen needs 8 valence electrons. So in total valence electrons, to make it happy, we have 1 carbon of 8 valence electrons, 2 hydrogens of 2 valence electrons, 1 oxygen of 8 valence electrons, which comes up with 20 valence electrons to be happy. In step 3, we're determining the number of bonds, which would be the number of bonds including what we did in step 2 and step 1 divided by 2, which was 20 valence electrons to make it happy minus 12 valence electrons divided by 2, which is 4 bonds. Step 4, we are choosing a central atom. And in this molecule, hydrogen is the least electronegative of the elements, but hydrogen is rarely the central atom in a molecule. So the next lowest electronegative atom is carbon. Step 5, we're going to draw the skeletal structure of the molecule, which we've determined that the central atom was going to be C. And then we connect the atoms with its actual bonds, which it has 4. But we only have 3 atoms left, which would make a double bond in one side to make 4 bonds. In order to get those connected, we determine which one would be the one for the double bond, and it would be oxygen and hydrogen for the other 2. Okay, so now for step 6, we're placing the electrons in the atoms, but we determined here that there is 8 valence electrons used from the 12 electrons of the actual molecule. There is 2, 4, 6, 8, which 12 minus 8 equals 4. Those 4 remaining valence electrons are going to be drawn at the end of oxygen, which concludes drawing the Lewis electron dot structure of formaldehyde, CH2O. So now we're going to talk about expanded valence shells, which are shells that expand to form more bonds only when they have empty orbitals that can hold additional pairs to release more energy. In order to explain that, we have the octet rule, which each atom wants to have 8 valence electrons. Valence electrons are atommost electrons used to form a bond to another atom.
Today we're going to be learning about electron configuration. We're going to start with aluminum. So aluminum says I am the 13th element in the periodic table, meaning that it has 13 electrons in it. So in order for me to go home, I have to go through the whole electron configuration in order to allow me to define which element I am or atom I am. And each of my atoms, neighbors, has different electrons which define each atom. Now I reside in my whole address, which is 1s2, 2s2, 2p6, 3s2, and 3p1. And that is my whole address for the electron configuration. A shortcut of my address, I have to start with my neighbor, which is neon, and that one holds 1s orbital, 2s orbital, and the 2p orbital. And I'm remaining with the 3s orbital and the 3p orbital. So I start with my neighbor neon and move to the 3s orbital, which takes 2 of my electrons. Then move on to the 3p orbital because I have 1 remaining electron. And that one takes 1 electron too. And now my new address, which is shortened, will be my noble gas neon and 3s orbital, 2 and 3p orbital 1. That's my new address, shortened address. After we're going to be learning about the covalent bonding theory, and we're going to start with beryllium chloride gas. And this is a covalent bond. And it's also known that this substance, the beryllium, doesn't follow the octet rule. We can see this by drawing that Lewis dot structure. And with this electrons, we put beryllium center. We have 2 chlorides outer, and we see that it requires 4 electrons, and we're left with 12 electrons. And we see each chlorine takes 6 electrons each, and that takes 12 electrons, meaning that beryllium has no electrons left to add, so it doesn't follow the octet rule. And this is called a electron deficiency.